while today you're sipping your nice cup of coffee, I will present you my research, which is entitled the Multimodal Framework for Tracking Pollutant Dispersion in the Mediterranean Sea. Just a brief introduction of my PhD. My PhD is an industrial one, and it's in collaboration between the University of Genova and ITT SPA. And the ultimate aim of my research is to create an user-friendly WebGIS interface that for oil spilling in the Mediterranean Sea. And at present, what I'm going to present to you is a structure, what we have created, that is capable of simulating and analyze how the dispersion evolves both in time and in space. You will see that we will divide the results into two cases. One is conducted only with the sea surface currents data, and the other one with other two components, and you will see why. But why it is important to study this kind of issue. Here we have an image that is taken from the EMODNet portal, and that shows us the routes per square kilometers per year. And as we can see, we have quite an intense maritime traffic in the Mediterranean, with values that reach up to 1,200 routes, where you have the red color. And we can see that mostly are near the coast. So the consequences of this large amount of maritime traffic leads often to a lot of consequences, and one of them is oil spilling. Here you have a map, a map with a graph associated, which show you the slicks that were detected between July 2020 and January 2024. In the graph, you have the spillage per month. And as you can see, there's quite a lot, because were detected approximately 757 oil slicks of different entities, of course. And the sources also can be various, for example, accidents, leaks from cargo, and more than often illegal discharges. And so there's a really urgent need to have an increase of accuracy in ocean prediction models, which is fundamental to improve oil spill response strategies and to then mitigate the environmental impacts. So what we have done to efficiently simulate the particle dispersion, we choose a Lagrangian particle tracking models, and itself to be operational, it makes use itself of the Python computer language through OceanParcels toolbox. This toolbox, OceanParcels, is really, really powerful because it allows the users to customize the codes in many ways. And how it works basically is that you have a certain amount of particles that are considered without mass, and you can select, for example, the number of particles, the size of the particles, where you want to release it, and even here you can select, for example, a point release or a continuous release, depending on your needs, of course. And to then make the particle start to move, we need an input variable, which is the velocity, of dispersion. So having all of these, we have here an example of how the outputs will be. And we can also from this evaluate other properties. And so we did. Initially, we evaluate the probability distribution, which correspond to a more to an experimental distribution in which you have the domain, the area selected divided into a grid, and then the particles that pass through the grid in time are counted and then divided by the total number of particles released at the initial instant. And this is really helpful to determine which area exhibits the higher concentration of particles. Then we evaluate the centroids of the clouds of particles moving in time. And by leaving the trace of the centroids in time, we have the trace that has followed the oil slicks. Then, with the value of the centroids, we can evaluate the dispersion that the particles undergo, and with respect to the centroid in time. And here we have the relative dispersion, which is the sum of the two components in x and y direction. And this gives us how the clouds of particles is spreading and in which direction. We then can evaluate other two components. One is the relative distance, which gives us the distance traveled by the whole oil slicks from the starting point to the end point, and the absolute distance that gives us the distance between the starting point and each point in time of the centroids. So having all these nice code, one for the simulation of dispersion and the other for the evaluation of the oil spill, we needed some real case to validate what we have created. And so we choose a real case scenario, in particular the one that occurred on 7 October 2018. At 7 a.m. between a cargo ship and a ferry. And this occurred off the coast of Corsica and caused the spillage of approximately 600 tons of oil. And so we wanted to compare and to test our structure here. So as I've previously mentioned, we will have two cases. The first case is considering the velocity of dispersion only equal to the sea surface current's velocity. And so to then make, of course, operational, we needed real data. And we choose to compare different ocean models that perform the sea surface currents. And why we chose that? The choice was dictated by, because ocean modeling is very complex, because it has lots of dynamics in the fluids, and which are extremely variable and complex. Also, there are also inaccuracy in the modeling due to, for example, the nonlinearity of equations that are used, empirically variables that are estimating, and other variables. So we chose three ocean models. All of these three models are open source, so it was easier for us to use the data. And the first model is the Copernicus Marine, which we will call CMEMS. The second one is the Ifremer, from the French Research Institute for the Exploitation of the Sea, and then the Shom, which is from the Naval Hydrographic and Oceanographic Service. Note that these three models have different spatial resolution, one from the other, and also one of them has a different temporal resolution. So we needed to take in account even that. Also the Copernicus, for the Copernicus and Ifremer, we had reanalysis data from the model, while from the Shom we didn't have the reanalysis, but we only had like the best forecast archive data. And so having all of these data, we could perform our first results. Here you have an animation which shows you the trajectory of the three oil slicks corresponding to the model associated. We have in blue the Copernicus, in green the Shom, and in orange the Ifremer one. And this, as we can clearly notice, the trajectories are quite different one from the other. And this is an interesting result because as we can see, we have used the same procedure to create the simulation for each model. And so the outputs are quite different. And moreover, from reports on this case, we had news that on the 16th October 2018, hydrocarbons were detected on the beach of Pamplon near Saint-Tropez. And this is like the specific time frame of our simulation on the 16th October. And you can see the point of impact, which is highlighted by the red dot. And we can see that clearly none of the three models reached the point by that time. And so only with few days of delay, we have the reaching of the point, but as we can see, the simulations are a bit inaccurate because there were other particles near other parts of the coast, which wasn't detected, and so on. So we needed to improve our simulation. And to do so, we add two other components to the sea surface currents. And one is the Stokes drift, which is caused by the surface waves, and the other one is the wind. These two components are associated with a coefficient, which is the alpha coefficient for the Stokes drift and the beta for the wind. And these two coefficient mitigate the effect of these two components. So even for this case, we needed other data. And to do so, we choose two other different models for the Stokes and the wind. And the first one is the ERA5, which has, as you can see, a really coarse spatial resolution, both for the ocean and for the atmosphere. And the other model that we have selected is the MeteOcean1, which is developed in the University of Genova by the research group with I'm working. And here we have a lower spatial, higher spatial resolution. And but the difference here is that in ERA5 model, we already had the evaluation of the Stokes drift, while for the MeteOcean model, we didn't have. So we evaluate that, we calculate with this formula using the variables that were already present in the model. So as we saw previously, we needed to choose a value for the alpha and beta coefficient, and we chose for alpha the value of 0.3 for all the three models, while for the beta coefficient we choose 0.02 for Siemens and Shom, while for Ifremer we have a slightly different one, which is 0.03. And I show you why this different in a few slides. So to evaluate these optimal values, we carried out a sensitivity analysis, which is based on the knowledge of the time of impact of the oil spills and when it reaches the French coast. So here we have the two results, and as we can already notice from the first instance, here the trajectory of the three simulations are already improving, having a more similar behavior one from the other. And so here again, knowing the date of impact on the French coast, we have the two time frame on the 16th October in the images below for the two models. And as we can see, these simulations are quite good because they reach the point by that time. We can see that for the MeteOcean was the optimal solution, while for the ERA5 with this coefficient, it is a good simulation, but it didn't quite reach the point exactly as the MeteOcean model. Here, I've made just a little bit of comparison with the first case, only using sea surface currents, and the second case, improving this with Stokes drift and wind. And as we can see, the difference is quite obvious. And to see that these two components, the Stokes drift and the wind, give a huge impact on the simulation. Here is another comparison on choosing the right coefficient, for example, because in the top figure, you can see that we performed the simulation for the three models with the same coefficients, using 0.03 for the alpha one and beta 0.02, but this wasn't performing quite well for the Ifremer model. And so we needed to adjust a little bit, and we saw that only adjusting like only one of the two coefficients, the beta one, the one from the wind, it was performing quite well. And you can see the results in the image below. Here, while testing different combination of output, we were curious to see also the output considering, for example, only the Stokes drift or only the wind effect. And on the top panel, you can see the combination of sea surface velocity with the Stokes drift. But here we, as we can see, we didn't have a quite good result. And on the bottom, instead, we have the image that shows us the results with the sea surface velocity and the wind. And we can see that here the simulation are a bit better than the one with the Stokes. And so what we can notice is that the simulation with the wind has more impact on the advective process, while with the one with the Stokes had a more diffusive process. And so we also compare, to better understand these outputs, the magnitude, the difference of magnitude of the Stokes drift and the wind. And here you have the two graphs. On the left, the one for the Stokes, and on the right, the one for the wind, for both of the two models, MeteOcean and ERA5, to see if they have consistency. And they have, but there's a huge difference in magnitude with the wind, which reaches almost up to 2 orders of magnitude more than the Stokes drift. And that's why it has a larger impact in the advective transport. Here, instead, we have other two graphs. On the left-hand side, we have the absolute distance in the continuous line and the relative distance in the dashed line for the three models. And here we can see that, for example, the Siemens models and the Ifremer models have a really similar behavior. And on the right-hand side, instead, we have the graph that shows us the relative dispersion, which is in the continuous line, and also the relative dispersion in the x direction, which is the dashed line, and in y direction, which is in the dotted line. And as you can see here, with this graph gives us an entity on the spreading that the particles had. And we can see that, for example, the Shom models had an order of magnitude more than with respect to the Siemens models. Another great source of information for us was the satellite images. Unfortunately, for this specific case, we only were able to detect the 3 images, 2 from the for the 8th October 2018 and 1 from the 9th October 2018. And these images are taken from Sentinel-1 satellite. And what we wanted to do was compare these images with our simulation, and how we recreate with QGIS the area of the oil slicks, which is the one in gray that you can see. And we compared with our simulation. What we did is to evaluate the centroids for the real case and our simulation. And with that, we could evaluate the distances between the centroids. And also we evaluate how many particles were detected inside the real area for each model. And here we have the results, and from the results we can see that the Siemens model is the one that mostly perform better the real case, because he has the lower distances between the barycenter and the higher percentage of particles detected inside the area, the real area of the oil slicks. So since my research is also in collaboration with ATT, part of my research has already been implemented in one of the tools that is developed by ATT, and the name is Simbad, which is a web platform for maritime professionals to improve the safety and operational efficiency. And so here you can see this tool in which you can I will start it again, in which you can select each point of your area where you want. You can select on the left the number of particles that you want to release, the diameter, and so on. This is a tool made in forecast, so it takes forecast data for now only from the Siemens models that we have seen for this, and it only considers by now the sea surface currents. So we want, of course, to improve these first results, and we will also add, this is just a mock-up on how it will be in the next future. We want to, of course, add the Stokes drift and the wind effect. And on the right-hand side, you will have the selection of the models that you want to use, different slider for coefficient depending on the needs, because the coefficient will be in a range that you can select. Also, the idea is to, of course, study the properties of the oil, because that affects a lot how the particles are behaving. And also, and finally, to have a more dynamic results, there will be also the possibility to click on a point and have the information on the simulation, having the graph, for example, of time and how the particles are spreading in that point. Also, another ongoing research that is part of my research is devoted to the 3D dispersion, and for that we are using by now the Copernicus Marine, which present data for the column of water. To do that, we adapted, to create the simulation, we adapted the code from the 2D to the 3D using OceanParcels. But in OceanParcels, to perform then the simulation, you need the value also of W, which is the vertical velocity. And in this case, we didn't have like the exact value of W for the model, and so we needed to estimate the vertical velocity. And how we do that? We have quite a few formula here, don't worry. We have firstly to apply the continuity equation, which ensures mass conservation. And note that for this preliminary analysis, we use only the simplified equation, not taking into account for now of the water. And to calculate the horizontal divergent, we use then the fourth order derivative, which is more, which we chose that because it's more accurate, and it reduces the numerical errors. And once we have the divergence, we can integrate it from the bottom to the surface to reconstruct then the vertical velocity. Here is the graph that shows you the preliminary output that we have obtained. Here, the particles are just moving with the currents. There's no other effect. You have the red cross that show you the start point, and then the particles that are floating around with the currents. So what we have seen, in summary, on my research, we have created a framework with Python, which is able to simulate the dispersion of oil spills using data from various models. We have seen from the case study that we have quite a difference between the models that simulates the seawater velocity. We have also a variability in output by choosing the of Stokes drift and wind, of course. And the ongoing research for the next year is going to be improving the simulation in 3D with OceanParcels, and also to study the characteristics of oil spills. And yeah, that's it. Thank you.